All right, so in the previous video we talked about gas laws, and I had left the last video with the equation PV equals nRT. This is called the ideal gas law, and I'd like to talk for just a couple of minutes how this equation was developed. So we've already talked about Boyle's law. Boyle's law results from the ideal gas equation. Remember, that's P1 V1 over T1 equals P2 V2 over T2, where subscript 1 is your initial condition and subscript 2 is your final condition. So under isothermal conditions where T1 is equal to T2, and so the T's effectively drop out of the combined gas law, we know that pressure times volume, regardless of when you measure it in a system, is always equal to a constant. Meaning when pressure goes up, volume goes down, proportional to one another. For example, if P2 is 3 times P1, then V1 is 3 times V2. So this is Boyle's law. So what this means is that when two physical observables are inversely proportional, they must be either in the numerator on the same side of the equation or both in the denominator of the same side of the equation. Notice that both P and V are on the same side of the equation and they're both in the numerator. They are inversely proportional. We also know from isobaric conditions, and since I've already reviewed these, but let's just go ahead and do these terms one more time. So isothermal conditions means that T1 is equal to T2, and so effectively they drop out of the combined gas law, which I've shown you in the upper right-hand portion of the screen. Now let's look at isobaric conditions. Isobaric conditions mean that P1 is equal to P2, and they drop out of the equation. And so at this point, I get Charles' law. Charles' law states that volume and temperature are directly proportional. Notice that V1 over T1 is V2 over T2. Now you can cross multiply these. You find they're directly proportional. Notice V1 and T1 would be on different sides of the equation, both in the numerator or both in the denominator. And you definitely see this with the ideal gas equation. Volume is in the numerator on the left-hand side of the equation. Temperature is in the numerator on the right-hand side of the equation. We can also have isochoric conditions. Students typically are not as familiar with isochoric as they are isothermal and isobaric, but isochoric means that V1 equals V2. And our equation will decompose to P1 over T1 is equal to P2 over T2. This is called Gay-Lussac's law. You have to understand, I did my undergraduate in the fine state of Mississippi. And so in Mississippi, this is pronounced Gay-Lussac. But let me give you a couple of reasons why we should not use that type of pronunciation. And this is the sad, sad story of Gay-Lussac. Gay-Lussac was a French nobleman during the French Revolution. Wrong place, wrong time, cited, of course, with King Louis XVI during the French Revolution, and like all noblemen, was summarily imprisoned and guillotined. Well, 3 days before Gay-Lussac's scheduled execution, Mrs. Gay-Lussac comes to see him in prison and informs him that she's been having a torrid love affair with Lord Kelvin. So just before Gay-Lussac lost his head, he lost his mind. So let's do the man a favor. It's Gay-Lussac, not Gay-Lussac. So P1 and T1 are directly proportional because if I were to cross multiply, both P1 and T1 would be in the numerator, but they would be on opposite sides of the equation. So if we come back and look at PV equals nRT, pressure is directly proportional to temperature. That's Gay-Lussac's law. Volume is directly proportional to temperature. That's Charles' law. Pressure is inversely proportional to volume. That's Boyle's law. What about the N? Well, again, this happens to be one of those little details that you lose in some courses. Volume is equal to some constant, and this constant later becomes the R gas constant times the number of moles. This is called Avogadro's law. Not to be confused with Avocado's law, which are really, really awesome. I make a killer guacamole. So Avogadro's law shows us that volume is directly proportional to the number of moles. In fact, at STP, we know that 1 mole is equal to 22.413 liters of substance. Of course, if it's not at STP, we just use the ideal gas law to determine the molar volume of a substance. This is for ideal gases. Remember, ideal gases are not real gases. We assume that there is, number one, no intermolecular forces between the molecules, and number two, the molecules themselves are points. They have no real volume. Both of these points were presented in a lot more detail on the previous video, so I would simply refer you back to that information. So with all 4 of these laws, Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law, we arrive with PV equals nRT. Now what I would like to do is to show you how we use PV equals nRT to solve questions that appear on both a PCAT and a DAT. So let's look at an example problem where I am given initial conditions for volume. The initial volume is 300 milliliters. The initial pressure is 1 atmosphere. The initial temperature is 25 degrees Celsius. And I'm going to go ahead and convert this to Kelvin because I never ever solve a gas law problem with any temperature scale other than Kelvin. Personally, I think we do this only so that we remember that Gay-Lussac's wife was a cheating dog. So these are our initial conditions. Our final conditions for volume, this is what we want to find. Our final pressure is 3 atmospheres. And our final temperature, like our initial temperature, is 25 degrees Celsius. Clearly what we have here is Boyle's law. Notice I have isothermal conditions. The initial temperature and the final temperature are the same. So if we go back to the combined gas law, these guys are the same, and P1V1 equals P2V2. Now I want to show you 2 ways of solving this problem. One is the easy way, and one is the hard way. I know that volume and pressure are inversely proportional. Pressure goes up by a factor of 3. 3 divided by 1 is 3. Therefore, the volume should go down by a factor of 3, and the answer will be 100 milliliters. That's the easy way to do the problem, and 100 milliliters is answer choice A, which is our credited response. If your brain doesn't operate in that sphere, then simply use P1 V1 equals P2 V2. V2 will be equal to P1 V1 divided by P2. This is going to be 300 milliliters times 1 atmosphere divided by 3 atmospheres. Atmospheres cancel. 300 divided by 3 is 100 milliliters. Now, a lot of people don't think that they can do the shortcut way, but let me take the time to explain this one more time. Boyle's law tells us that volume and pressure are inversely proportional. That means that P times V is always equal to the same number. PV equals a constant. In this case, our constant is 300. 3 times what number is 300? Obvious answer is 100. The pressure goes up by a factor of 3, and I get a factor of 3 by dividing the final pressure by the initial pressure. So since the pressure goes up by a factor of 3, this only results when I squeeze the molecules closer together. So the volume must decrease. The volume goes down by a factor of 3. 300 divided by 3 is, yes, you guessed it, 100 mils. So it's 3 different approaches to solving that problem. Okay, let's move on to another problem. If both the pressure and the temperature of a particular gas sample were doubled, what would be the effect on volume? Notice there's no reference in this question to the number of moles. So let's go combine gas law one more time. So we're looking at P1 V1 over T1 equals P2 V2 over T2. My preference in a problem like this is to choose values. So let's say that P1 is equal to 2 atmospheres and P2, which is doubled relative to P1, is 4 atmospheres. Let's V1, let's call V1 5 liters, and V2 is what we're looking for. We don't know what it is. T1, let's say it's 250 Kelvin. And T2, let's say it's 500 Kelvin. And now rather than dealing with variables, I'm dealing with numbers. So I have 2 times 5 over 250 equals 4 times V2 over 500. There's a variety of ways that we can solve this. One way that is effective is just to reduce our fraction. 2 over 250, both of those can be divided by 2. That would leave me with 5 over 125 equals, now I can divide both 4 and 500 by 4. That would leave me with V2 over 125. So clearly V2 does not change. It is 5 liters. That's one way that you could solve it. Another way, and this one's going to be a little bit more algebraically intensive, rather than saying V2, I could say 2 times V1. And instead of saying T2, I could say 2 times T1. Notice what happens. The V1s, they're on both sides of the equation. They're both in numerators. They cancel. The T1s, they're both in denominators on both sides of the equation. They cancel. And I made a small mistake here, so let me go back and fix this. It's P2 that is 2 times P1. So let me erase what I did right here. V2, V1. P2 is 2 times P1. And so it is the 2 P1s that cancel. And 2 over 2, those also cancel. What do I get? V1 is equal to V2. There is no change in volume. Now, let me read the answer choices for this particular problem. A, the volume would quadruple. That's obviously incorrect. The volume would decrease by a factor of 4. That's incorrect. The volume would double. That's incorrect. The volume would remain the same. That is the credited response. So in this particular question, the credited response is answer choice D.